So complex designs are a little tricky, and I'm going to do something a little bit different for this chapter. Rather than narrate the slides for you, I'm going to instead walk you through an example like you'll have on tests and assignments, just to give you a sense of exactly what you should be able to do and what I will give you. So this is an example of stretching exercises in your book. This is a cognitive psychology study that's looking at the reaction time. So the reaction time is our dependent variable. We know this because it's on the y-axis of the graph of the data that they gave us. And then we have two independent variables. There was a time delay. Some people got 30 seconds, other people got 60 seconds. And then the other independent variable is pattern complexity. And some people got simple patterns and some people got complex patterns. So we've got a 2x2 design, two independent variables with two levels each. Up until now, we've been looking at data mostly given to us in the tables, but you can do the exact same information with data that's given to you in a graph like this. So what you need to remember is that each point on the graph indicates a mean for each group. So for example, this point tells us about the mean for participants who had a 30-second delay who saw the simple stimulus. This point up here is the mean for participants who saw the complex stimulus and a 60-second delay. So we have all of the information we need to put this data in. So to begin with, we know that we have our two independent variables, pattern complexity and delay, and we've got two levels of each. So I can set up the table before I do anything with my numbers. I've got delay, 30 and 60 seconds, and pattern complexities with our two levels, simple and complex. So as I said, each dot represents a mean. So we can look at the dot that's indicated here. It's for simple pattern at 30 seconds delays, and it looks like that's about 525 in terms of the reaction time. So I can transfer that to my table to the appropriate box for the condition that got a simple pattern design with the, or simple pattern complexity with a 30. So I'm still going to stay on the simple line and just go to the second dot. So for the group that had a simple pattern complexity, but a 60-second delay, it looks like the mean is about 575. So again, I can just transfer that into. Now I've moved on to the complex independent variable, or to the complex condition of the pattern complexity independent variable. For those who had complex and a 30-second delay, it looks like our mean is about 550. And for those who had the complex design and a 60-second delay, it looks like the mean was about 750. Most of the examples I give you will not start out as a graph. Instead, you're going to have to go convert the data from the table and convert it into a. The pattern is essentially the same. What you do is you just do it in reverse. So you need to first determine which independent variable will be on the graph on the x-axis and which is going to be represented by either a solid or a dotted line. And just transfer the data on there. So I'd start with the one that's aligned. So let's say you want to graph the level simple of pattern complexity. You draw a dot for your mean in the 30-second group and another dot for your mean in the 60-second group and connect them with the line. Okay, so now that we've got our data in a table, the next thing we need to do, the first thing we're going to do is look at mean effects for each independent variable. And we'll start with pattern complexity. So the first thing I need to think about is if I'm testing the mean effects for pattern complexity, what groups am I interested in? What I really want to know is the difference between simple and complex patterns, regardless of delay. So I don't care about delay. So I'm just going to look at simple versus complex averaged across delay. So again, I'm going to average down because I'm looking for the mean overall for simple versus complex patterns. So I'm going to take my averages. I get a mean of 550 for the simple group and a mean of 650 for the complex group. It means it looks like there's a pretty substantial difference, suggesting that there is a mean effect. And when I look at the differences between the two numbers, it looks like the complex pattern group has a slower reaction time than the simple pattern group. I just want to point out here that what I did when I described what was happening is I brought back in our dependent variable. It's really important when I ask you to interpret something that you go back and think about what does this mean in terms of the specific independent or dependent variables that are studied. So in this case, our dependent variable is reaction time. So what I can say is regardless of delay, the complex group had a longer reaction time than the simple group. But we've got two independent variables, which means that we have two main effects. So the second one is for delay. For the main effect delay, I want to know the difference between 30-second group and the 60-second group. And again, I'm not interested in pattern complexity for this one, so I'm going to average across pattern complexity to get the mean for the 30-second group and the mean for the 60-second group. Again, it looks like we might have another main effect here going on, with the 60-second delay group having a slower reaction time, meaning a longer amount of time compared to the 60-second. And again, I've got to go back to my dependent variable. So I can say regardless of complexity, the 60-second group had longer reaction times than the 30-second group. Okay, so I've tested my main effects. I know that there are two main effects. Now I want to move on to the interaction. So remember that with the interaction, what we're looking at is do the effects of one independent variable differ depending on the levels of another. So for this example, we might ask, do the effects of delay differ depending on the level of pattern complexity? Now, if you'll remember looking back at the graph that I gave you originally with the data, the lines weren't parallel, which means we might suspect that there's an interaction. But we're going to officially test this by using the subtraction. So for this example, we're going to subtract the lower numbers from the upper numbers. Remember that it doesn't matter. You could go across two. So we're going to look at the difference between the 30-second and 60-second delay groups in simple pattern complexity and the difference between 30 and 60-second delay in complex pattern complexity. And remember that with the subtraction method, we're looking to see whether there are differences between the differences, basically. So here we got a difference of -50 versus -20. That's a pretty big difference. It's telling us that the effects of delay are not the same at the two levels of pattern complexity. So the fact that these two numbers we got during our subtraction method are not the same suggests that we do have an interaction. Now, in order to really interpret this interaction, we have to go back to our. So again, this is the same figure you've all already seen, just reminding you that each number in the table is a point on the graph. And again, remember that your dependent variable always goes on the y-axis when you're graphing something. So our dependent variable is reaction time, and you can see it up in the graph. One independent variable goes on the x-axis, and it's arbitrary which one you choose. So either one can go there. In this case, we have delay on the x-axis with one column, if you will, for 30-second delay, another one for 60-second delay. And then the other independent variable is indicated by a solid or a dotted line. And you need a key or you need to label the line so that your reader can know. Okay, so because the lines aren't parallel, it again suggests that there is an interaction effect. Now I just want to note, the easiest way to tell if there's an interaction effect is if the lines cross. However, even if they don't actually cross on the graph, if they continued on to infinity, if they would at some point cross, we say that they're not parallel, and that suggests an interaction effect. So we've proven through our graph and through the subtraction method that there does seem to be an interaction effect. Now we need to interpret it, and we need to interpret this through our simple main effects. So remember that for simple main effects, what we're doing is we're picking one of the independent variables to focus on and describing what's happening with the other independent variable at each level of our focus independent variable. So let me walk you through. Now I think it's easiest to start with the independent variable that's on the x-axis. So let's do that. So what we're going to do is we're going to describe what's happening at the 30-second delay and then move on to what's happening at the 60-second delay. You need to describe both parts, but by breaking it up, you'll get all of the information you need. So at 30 seconds, there's only a small difference in reaction time between the simple and complex tasks. They're essentially the same. So at a 30-second delay, participants had very similar reaction times for both simple and complex patterns. Again, we're describing what's happening at one level of delay for both levels of complexity. Now we have to describe what's happening at the 60-second delay. And again, we need both to fully understand the interaction. So what we can see is at the 60-second delay, people have much slower reaction times or much longer reaction times compared to, in complex patterns compared to simple patterns. So what this means is that the effect of pattern differs depending on the amount of delay people have before responding. So at the 60-second delay, participants have much longer reaction times to complex patterns than to a simple pattern. So all of this together is essentially what you should be able to do if I give you a table or a line graph and ask you to interpret the interaction. I'll ask you to go through step by step, but you need to know how to do each step. You need to be able to convert from a line graph to a table and back. You need to be able to calculate and interpret the main effects. And again, by interpretation, I mean explaining what's going on in terms of the independent variable and the dependent variable being studied. You should also be sure to indicate which one is higher or lower. Don't just say that they're different. And then you need to be able to use the subtraction method to know how to look for interactions in line graphs. Or to know how to look for interactions, and also you need to know how to look for interactions in line graphs as well. And then you need to be able to interpret the interactions by looking at the simple main effects.